we can start. Everything is a demo. And the goal is to show how joins work. And we will show exactly how it works by slowing down and putting breakpoints with GDB on the join execution. So I will need only small tables, the Scott tables, and I will do a very simple join. We don't see the screen below. And I just set up everything with splitting my screen. I will execute the query on the top, and we will see the plan in the middle. I will show the plan with SQL Monitor. Yeah, it takes a bit more space than expected, but that will be fine. So with SQL Monitor, we can look at the execution of a statement while it is running. You can use it in Flash or you can use it in the text mode. Here I'm using SQL CL with a repeat command so that it can refresh the display every second. And basically, I will run some queries forcing the join method with ints. Here I force a nested loop between those two tables, and we will see that the plan is a nested loop. If I do a hash join, we will see a hash join there. Hash join with the AMP table first. We will detail them later. This is just to show the different kind of join we will see. We will also see a merge join there, and the plan will be a merge join. Now, this goes too fast to show exactly how it works. So I will split my screen again and open something else, just getting the SID of the session on the top. I copy that and I split my screen again. And here I will run GDB, the debugger, on the process of my session that I got above from the $session. Here it is. I am attached to the running session. And I will set some breakpoints on different functions where I know the join goes through the function to understand and to stop at those points. So basically, the first one I will set OPI fetch. That's the fetch call. When the client fetches rows, we see the OPI fetch on the server. And then I will set breakpoints on functions starting with QER, query execution resource. Those QER functions are all the functions running behind the different operations of the plan. Each line of the plan is an operation, and behind there are C functions in the Oracle code running that. Here I have set a lot of QER TB something, TB for table. Those are the functions running when we are in a table access full scan. I have also some function QER IX. This is for index access. Joins, for the operations that are joins, we have function as QER GO. How do you know the name of the function? You ask to tunnel podder, Fritz-Gland. You can find some of them in support notes. Or you just debug and look at the backtrace to try to find the functions. All QER ones are the execution of the plan operations. Hash join are not GO, but HN. So I have many of them. We will see when, during the execution, when they are called. And SO for the sort operation. For example, here we see a buffer sort. There are some functions QER SO behind them. Gather statistic, because at the end, I will show you what happens with adaptive plans. And we will see that there are some functions that gather statistics, GS. I'm going quick on that. SC, the statistic collector, we will see that. And for adaptive plan, we will see those functions that disables a plan or enables another. So everything is set. I have a lot of breakpoints. Then when I will run a query on the top, it will stop on the breakpoint, and we will see where in the middle. The middle one is a bit large. We will see how it's displayed. So at the top, I run a join from det to amp. I'm forcing a nested loop. I'm forcing the optimizer to start by det and then going to amp with a nested loop. We don't see yet the execution because GDB is stopping, and in GDB, I will just continue to the next breakpoint. And there it stops on a start function in QARGO, which is GO for join, the join operation. The start is kind of initialization of all operations. So basically the plan is executed from the top. The fetch call was there, then it goes to nested loop. And if I continue, I have the start that is propagated to the table part. And then we are in the fetch. Now I go to the next one. The fetch received by the execution will be propagated to the operation. Here we are there. So here with SQL Monitor, you see what is currently active. It looks like it is active in CPU. Actually, I stopped on the breakpoint. So for Oracle, it has something to run in CPU. The fetch then propagated there and propagated to the first child, the table access here, depth. So my fetch call has to read first from depth. This is where you see where Oracle starts in the execution plan. Then you see the start, the initialization of the second one. So here it looks like at the first call, Oracle has initialized everything, but not yet this one. Probably an optimization. In case there is no row in depth, there is no reason to initialize the other one. So here it is initialized. We are there. Basically, we have read one row from depth, and we are now going to amp. Now being in the fetch for amp, getting the rows from there, and then we have a row. We have one row from depth. There is a matching row from amp. We have to return that row. I went fast, but I set array size to 1 to fetch the rows one by one to see exactly what happens. And then we have some release function for the different operation. For the join, release just will probably release some structures in memory before sending back the row. And here it is, my row came there. And my client now is fetching the next row. So I stop on the fetch call here for the select, and I continue. This fetch is propagated to the child operation, the join, and then this is propagated to the table here. I still have one row from depth. I have found one row in AMP, but maybe I have more employees in this department. So the second fetch goes directly there to see if there are still some AMP for this depth. I continue this and I go fast on that, and we can see that the row number from SQL Monitor, not easy to see it. I have 3 rows from that. Where are the rows? I may increase the size here. Yeah. With SQL Monitor, you see the number of execution of each operation. So 2 times because it's a loop here, and the number of rows returned there. So here you see that nested loop will read rows from the first table, and then we'll find the rows doing a second loop on the other one. This is why it's called nested loop. And I continue to the end. So looking at the number of rows, I have here 3 rows coming from depth, 14 from AMP. So we are near the end because I know that we have 14 employees. The rows are coming there each time. And here we go. Now we see some functions. So we have our 14 rows. I'm sorry, the screen is a bit small, but the 14 rows are there. And now close operation for all these operations. And then my query is finished, 14 rows selected. So this is how a nested loop works. And you can see exactly how it works internally. And you can also see exactly when the things are initialized with the start function and closed at the end. So that was nested loop, quite simple. I will now run a hash join. So here is how you can int a hash join. I start with depth. I use a hash join to go to AMP. And because I want to keep depth first, being the hash table, I just add no swap join. If I do not add that, the optimizer has the possibility to inverse those things. So here we will see a hash join. I will disable some breakpoint for the moment because there's something new in 12.2 where before executing the query, there are some recursive executions done. And that's new. Usually the recursive query occurs only at pass time. In 12.2, and because of an in-memory feature, they run some queries on the dictionary, which is considered as a bug, and they will change that because when in-memory size is 0, that should not happen. So just let me remove some breakpoints and continue. Sometimes you have some segmentation fault when you do GDB. That's not a big problem. I'm just checking where we are. We are at the start. I will just zoom it because I don't see that on that screen, the backtrace. I wanted to check if I am in a recursive operation, but not in this case, so I can re-enable the breakpoints. And we will continue on that. Where are we? The call has been propagated to the hash join, and we are executing the hash join. Okay. So finally, something is different than expected. I can see here fetch by row ID. This is an access by index, and that's probably the recursive query I was talking about. Unfortunately, if I backtrace, I expected just to see some RPI. Yeah, they are there, but the screen was too small. Recursive queries, I can see RPI in the backtrace. So I will just continue to disable some breakpoints, enable only the fetch call. And continue when I'm sure that I have no RPI something in the backtrace, so that I'm not in a recursive query, but really actually in my query. And this is the case. Then I enable all breakpoints because I want to stop everywhere. And we can see that for the moment, I stopped on the fetch call. I am in the select statement here. If I continue, the fetch call will be propagated to hash join, query hash join fetch. This is propagated to the table, the first table child of the hash join here with a fetch. And we can see a function query chain. So for hash join, pack, 1 call, 2 call, 3 calls, 4 calls. I have 4 rows in depth. It seems that it has read the 4 rows and packed them. Actually, it doesn't build immediately the hash table, just puts in memory to be able to pack them. And if I continue the execution, table fetch, the second one. So I have the rows from depth that are packed somewhere in memory. Then it can start to read amp to try to match the rows there. I continue, build hash table. So it seems that everything is packed but not yet built. Build takes a bit of CPU, so probably if there were no row in amp, there is no reason to build the whole hash table. Now that it knows that there is one row fetch from that, build hash table with some allocation and the probe choose something. This is when really the matching is done from the row read from amp and matching the one from the hash table, and the row was written there. So in a hash join, before being able to return the first row, a lot of work has to be done to read all the rows from the first child and pack them and hash them and return the row. Then when this is done, it is exactly like a nested loop where it can read. So the next fetch is propagated to the amp here, and the next row is read and will be compared with the hash table and will return it. I let it running, you see the same. So the hash join, the start of hash join is quite long. It builds a structure where it will be easier to do the join later. The difference, nested loop, I did a nested loop with full scan. Usually a nested loop will go through index to the second one. The idea is that the nested loop will use a structure sorted or hashed before. The hash join will build the structure just for that join. And the clause and the rows are written there. I will run again a hash join, but with the opposite. Use hash, but instead of no swap join, I have a swap join input, which will put the amp table first here. The amp table will be the hashed table here. So as before, I disable all breakpoints except the first one, which is the fetch call, because of those recursive query. I continue, I check the backtrace. I'm still in a recursive query there. I continue, I'm still in a recursive query. This is quite annoying, but okay. I can enable the breakpoints and continue. And we are in the query fetch call. Not yet. Because this is an access by index and I know I have no index, that's probably another recursive query that is coming there. So again, I will disable all the breakpoint except the one. This should be okay now. I increase the screen, no RPI call, so that should be the right one. If I continue, I have the fetch call. The fetch call is on the select set statement. That looks okay. I enable all breakpoints. I continue, and the fetch has been propagated. Where's the number of rows there? I think I missed the part where this table was built, but the idea is that amp here is read with 14 rows. We should see 14 rows there, and depth is read then. The optimizer will probably choose the smaller table as the first one, because it's the smaller, it has more probability to fit in memory. If it doesn't fit in memory, that will be swapped to temp and take some IO when doing the join. Okay, so I will go quickly on this one because then it's the same and the query is finished. 14 rows selected there. And we will have a look at the next one, which will be a merge join with the int use merge. So the idea of the merge join, like a hash join, the execution will start by creating some structure to get the join faster later. Then in that case, it will read depth, sort it, it will read amp, sort it, and once both inputs are sorted, it's easier to get the rows one by one matching instead of reading the whole structure behind. So this is done. I continue there. I have some fetch calls that are propagated. Here we are the join. Sorry, the screen is really small there. So the call was propagated, merge join to the sort join to the function QRSO something, where the row will be sorted. We have to fetch them. It's a fetch simple there. And table fetch, we are reading the rows. 1, 2, 3, 4. That's 4 rows fetched and sorted in the sort join buffer. And then once that's done, the other part will be run, reading the 14 rows there, sorting them. QR SO fetch, I should have 14 of them here. Compare is probably the function that will compare once sorted to get what is matching from the top of them, and join release, and then the first row can come out. So that's quite long to get the first row with that. Both inputs must be sorted. But when it's done, then the join is very easy. If the access were not a full scan, but an index scan, then the row may be already sorted. And this sort operation doesn't take a lot of resource. And this is a case where sort join can be chosen. Another case where you can see sort join instead of hash join, if you do not have an equality in the join predicate, but an inequality, this can be done only with a sort join. You cannot use a hash function to know if a value is larger than another one, only equality. Okay, so I will just continue until the end of this one. And slowing that, all that, we see the rows returning, the fetch call. It was not running anymore because here my repeat command from SQL CL has stopped. I have to run it again. And this is why in SQL Monitor, you see exactly which operation is active there. So we are here in the sort join, but it's already sorted. It's just calling the function and the rows goes from there. In the execution plan, the rows from an operation are returned to the operation above. And we can see exactly that through the functions there. How many rows do I have here? 14, 14, so that's near the end. Yes, 14 there. Okay, then last type of join, which is not really a type of join that you can find everywhere, the merge join. I will just some water to continue. So here I have a hint, use merge Cartesian. I didn't run the same query with no predicate to be sure to have a Cartesian join. Here I am in 19C until 12.1, the query before with the join can be run as a merge join Cartesian just with the hint. They have probably disabled that. And currently, this kind of query can be forced only if I'm really doing a cross join. This is the ANSI syntax for the cross join. So here the result will not be the same. I will not get 14 rows, but 4 times 14. So let's running, and I will do the same, not to get this recursive query. I will try to get it correctly. Yeah, we see RPI something that is the recursive one. We are still in recursive query. I cannot really predict the number of recursive queries that I run. It's something that should not be run in this case because I'm not in memory. Again. Okay. This is a fetch call. Fetch trace. I said that I cannot really predict, and I have never seen so many queries like that. If I continue, I check the backtrace. Okay, I will just continue a while, and maybe we will go beyond. Okay, maybe too fast, but that's not a problem. I just re-enable my breakpoints. So one important thing in the merge join Cartesian, so you can see the two child, the two tables, and one has a buffer sort operation on it. It will not sort anything. The buffer sort name is there because probably it uses the same code as the sort. Here the idea is just to buffer. Merge join Cartesian for each row from the first table, the outer table. For each row, it will read the second table. But instead of doing a full scan each time, the first time it will read it, it will put it in a buffer, and then it will read a buffer, but from the beginning to the end. Different from the sort merge join where it is read only to the current position because it is sorted. So we should see that propagating the fetch call from the select to the merge, then to the first child, the access. Here we fetch one row from depth, fetch simple. I have 4 rows from depth. I just expected that the buffer is read there. Yeah. Maybe I went too fast. How many executions here? No, that was the first execution here. So the table was read once. You can see the number of execution of the operation there. And put in the buffer. And then only the buffer is read.
Sorry?
She does want to go with us.
Oh, when we're going?
Yeah. And I really honestly wouldn't mind walking because my legs need to walk a little bit more today.
Okay, so we have a lot of rows because that's a merge join Cartesian. I just don't see, we should see, but we will see that at the end. What I will do, I will just disable the breakpoints and continue up to the end, and then we will see the full plan where the statistics are up to date with the execution. Yeah, this is the point I wanted to show you. Number of execution of each operation. I have 4 rows coming from the depth, and I have only one execution here for the full scan, but for execution for the buffer sorts. So only the first execution did read the rows, they were in the buffer, and then the next execution were there. With SQL Monitor, you can really understand what happens at the different steps. Okay, so now the most interesting will be adaptive plans that came in 12c, where the optimizer can choose the plan at execution time. So here I am running a different query, you see at the top. A query with a strange predicate. The idea is that the optimizer has no clue that all salaries there have a 0 at the end. This is something I know, knowing the data. The optimizer has no statistics telling that. So I'm running a query where the optimizer, even with the best statistics, cannot guess the number of rows coming from this predicate. As before, I disabled the breakpoints to go through the recursive query. I hope I will not have as much as before. That looks good. So I am in the execution, stopped on the fetch call at the top. Here you can see the execution plan where I'm still joining only two tables, AMP and dep. And you can see many occurrences of them. And you can see some nested loop and some hash join. At past time, the optimizer has just built a plan with the possibility to do a nested loop and a possibility to do a hash join. And we see both of them in the plan. Here. If I run it, so I continue, the fetch call will be propagated to all steps. So always from the top to the first child. If I continue there, it doesn't look to be running. Okay, propagated to the hash join, nested loop. You know that I think since 11G, the nested loops, we can see two operations. So this is propagated. And I can see new functions where I have breakpoints, but we haven't seen them before. This function is in the nested loop operation, QERGO, and we have something that is resolve dynamic. Those functions are there because this nested loop is a special nested loop where something can be resolved dynamically according to the name. I just continue, the propagation goes to QERSC something, statistic collector. I continue, we have a fetch, but fetch buffer. Looks like the rows will be buffered there. And finally, this is a function that reads the row from AMP. Here, what Oracle will do, because it is an adaptive plan, it will start as a nested loop and will read, fetch the rows from AMP, buffer them in the statistic collector, count them, and if the number of rows is a lot bigger than expected, the execution has the possibility to switch. The nested loop was planned because the estimation was low. If I reduce that, we can see, okay, the first column is the estimation. So we can see that the estimation of the number of rows was 1 here. And at execution time, it can decide if the number of rows is bigger, it can decide to go to hash join and then do the hash join that is before. So I am still in the fetch of the first row there. And this row goes back to the statistic collector with a function starting with buffer something. I continue, update statistics, probably just counting the rows. Another buffer, update statistic. So the rows were fetched. and buffered. Nothing is written. I still have a fetch size of 1, but nothing is written for the moment. And we can see that after 4 rows there, we have a function with a fire action, still fire action, and in the statistic collector, still something DP resolve, dynamic plan resolve. So it counts, it buffers the rows, it counts the rows, and it can take an action, fire an action, such as resolving the join method. And the name of the function is clear here, disable nested loop. It started as a nested loop because the estimation was 1 row, and for 1 row, the nested loop is better, only 1 loop. And buffering the rows decided that it's better to disable the nested loop. And we can see the pack function for the hash join. So I have a few rows buffered. I disable the nested loops, then those rows will start to be packed to be the hash table there. Instead of doing a nested loop from amp to depth by index, this will put all rows from amp in the hash function and do a hash join with the other one. It continues to fetch rows because they were buffered, but maybe not all of them. As soon as there are too many rows and the plan is solved to be a hash join, then the nested loop is disabled, and then no need to buffer anymore. So more rows read there and packed in the hash join. Updating statistics, pack. So that's even longer to initialize. It can still return no rows for the moment. It has to build the hash table. Build hash table. So they were packed, and then it reads depth, and it build the hash table. And we have seen a probe choose, and this is where the first row will be able to be returned, releasing everything, and at the top we should see soon the first row coming there. So a longer initialization, but to be sure to get the right join method in case of misestimation of the cardinality. Then we continue, and then that will be faster because some rows were already buffered and the hash table is built. So now it's just running like a hash join, and I'm going fast on that. This is exactly the same, and you see rows returned there. I will show you one more thing on these adaptive plans. And for that, I do not need anymore to stop with breakpoints. So I remove all my breakpoints. Continue. I will even close this one, and I will show you again. I flushed the shared pool because this resolution is done only at the first execution. Now, if I run it again, it will run with a hash join directly. So I flush the shared pool, and I will run the query again, but first I will do an explain plan. Explain plan for exactly the same query. And I will display the plan, just zooming that. So this is the plan we see when we do an explain plan. The same as before, you see some hash join and nested loop, but with the adaptive format, I have the information about the branches that are disabled. Here, I do an explain plan at parse time, at optimization time. The optimizer chooses a nested loop because it estimates 1 row. So better do just 1 loop rather than trying to build a hash table with that. So at first, the hash join part is disabled, which means that hash join here is disabled, and the full scan in case of hash join is disabled. What is enabled is nested loop and index access to the second table. So this is explain plan at parse time, optimization time. And now I will run it with SQL Monitor, and I will display the plan from the cursor now that it is executed with the BMS explain display and still with the plus adaptive format. I zoom that, and here basically you see the same, except that the minus sign are not in front of the hash join and the full scan. They are in front of the part of the nested loop one, index access and nested loop. So after the first execution, the plan is resolved, and in this case, with another join method. And one additional thing, so we have seen that the rows are counted. So at execution time, the engine must know the threshold where the optimizer thinks that there are too many rows for a nested loop and it's better to do hash join. Here I will get the CBO trace, the 10053 trace. So I just get my trace file for my session and get the trace with the BMS SQL trace. So this, actually this will reparse the statement and dumps all the debug information of the optimizer. I will not show the big trace like that. I will just grab on the lines that are interesting for me. So I will grab on lines starting with DP or AP, dynamic plan, adaptive plans, which is quite the same, probably two different names. So I grab that and I will zoom on it to show you what we have in the trace, starting with AP and DP. At the end, I can see something quite explicit. Find point of inflection for nested loop join versus hash join, cardinality 3.2. If you remember, I had a lot of rows coming from AMP, but the optimizer estimated to 1. And when we run it, I had 4 rows read before that decision that fire action, resolve anything. This is because of this threshold. When reading 3 rows, you don't know if you are above the threshold. At the 4th row, then the decision, nested loop is not so good, hash join is better in this case. And before, we can see how this point was determined, just checking for different cardinalities. What if I have 100 of rows coming from the first table? What if 56? What if each time dichotomy divided by 2 until it finds the point of inflection where the optimizer think it's better to do a hash join for that. This is given to the execution, and the statistic collector will buffer the rows, count the rows, and take the decision. Just one important thing, this buffer has a limit. And sometimes if the estimation is really, really, really bad, sometimes it can keep the nested loop, not because the number of rows is small, just because it doesn't fit in the buffer. And then this idea of adaptive plan is just forgotten. That can be a problem with it. Okay, so this is all I wanted to show. The idea is that you can see how it works even without running on very big table and looking at the SQL Monitor during hours. If you want to know the name of the, I can show you. Fritz Ugland and Kamil from Poland did something very nice. In oh, you don't see my screen here. I will put that in OAFN.info. You just type the name of a function, for example, QERSC something, and you can see the definition. So Fritz-Hoagland is when he knows what a function is doing, is putting a small description on it, and this is very useful when we try to understand. This is kind of reverse engineering the hierarchical functions. Okay, do you have questions?